So next we have Andrew Brower. Andrew Brower is an assistant professor at University of Michigan, where he does a lot of computational modeling of various types of diseases, including infectious and chronic disease. I think he's going to talk to us about WASH interventions.
Thank you very much. I'll wait here a second for these slides. But we're going to take a turn here away from environmental surveillance to enterics, and in particular thinking about how do we interpret the field of water sanitation and hygiene interventions, and how we take the heterogeneity that's been across many different types of studies and think about the underlying factors that are driving that heterogeneity, and also generalize kind of going forward. So I'll stop vamping for a second and wait for the slides. Great. So to my talk, I'm going to share a mechanistic model and a web-based tool to estimate the potential impact of water sanitation hygiene interventions, accounting for both contextual and intervention factors. Ooh, let's see if it, wonderful. Okay, great. So what we know is that water sanitation hygiene interventions do have a lot of potential to reduce diarrheal disease burden in low resource settings. So this tiny little figure on the left comes from a meta-analysis looking at hygiene interventions, and they concluded that, over all of these studies, there is kind of a robust understanding that we have the potential for reduced diarrheal disease. Unfortunately, there's also really large heterogeneity across these studies, and many particularly large, well-run trials recently came with kind of modest to null results. And these include, for example, the WASH Benefits Bangladesh study, which found no significant difference in the water intervention, only a modest improvement for hygiene and sanitation versus the control arm, and no complementarity. So there was no additional benefit of combining different types of interventions. And this flies in the face of what we know that what WASH can do. So what's going on here? So what are the factors that may be contributing to the heterogeneity and kind of lack of consistency in the results? So could it be just efficacy? Is it that the interventions don't work as well as we think they do? Is it compliance? Are people actually getting the interventions as intended? And are they using them as intended? Community coverage. So we know that there are indirect protection from these interventions. So how much of the community is actually covered by the interventions? Are we taking account indirect protection? Are we not? How much of the transmission is actually being blocked? So these are a diverse set of pathogens. They cover a diverse set of transmission pathways. Most of these water sanitation hygiene are only focusing on things like water and maybe Hansen fomites, but they're not focusing on animals necessarily or food. We also have contextual factors like the base WASH condition. So did participants already have baseline WASH infrastructure, and so that the new intervention is not a huge increase? And then how much does the baseline disease conditions affect? So what is the prevalence of diarrhea at the site? Does the effectiveness depend on the disease burden? So we're probably going to think about the top three as intervention factors, which are at least somewhat modifiable by the investigators. The bottom two is contextual factors that really depend on the location. And completeness is somewhere in between, where it's a little bit modifiable and a little bit dependent on the location. And in particular, all of these factors may be driven by differences in pathogen distributions. So different pathogens are going to use different transmission pathways. Some of them may be more person to person. Some of them may be more driven by food or by animals. And the interventions are going to have different efficacies. So, for example, chlorination is more effective against bacteria and viruses and less effective against protozoa, generally speaking. And if we look at, for example, results from the Global Enteric Multi-Center Study, or GEMS, they found pretty substantial differences in the distribution of pathogens between sites. So, big differences here in Cryptosporidium, Shigella, ST, ETEC, norovirus, cholera, for example. And so what we hope to do here is develop a mechanistic transmission framework to predict and generalize watch trial outcomes accounting for these factors. So I'm not going to go into a lot of details technically here, but we're going to think about our model accounting for people both that are using the intervention and that are not. So we'll have a kind of SIS framework for people that do not have the intervention or comparable initial baseline conditions. There'll be our regular exposure population, and those that do have the intervention or kind of equivalent conditions, an attenuated exposure population. We need to account for a shared environment so that these two populations are not independent. They are interacting through environment in kind of, this is if we're looking at watch benefits Bangladesh, for example, in terms of a compound of multiple households. And we might want to account for both the environments that we are intervening on and the environments that we are not intervening on, at least at a theoretical level. We also have to account for intervention compliance and baseline conditions. This is an example from the Watch Benefits Bangladesh, again, where we see the fraction of people with an intervention grade latrine. And even before the study starts, at baseline, about 25% of households already have a latrine that was equivalent substantively to what the intervention is providing. Then, of course, we get over 90% compliance in the midline and end line. That, of course, is not always the case for a lot of these trials, and so accounting for the actual compliance is important. To kind of demonstrate this, I'm going to show you a couple of scenarios here where I'm picking higher or lower values for each of these. This is not a complete kind of parameter search, but just to give a little bit of a flavor of how sensitivity to these different factors may depend on the other parameters as a whole. So I'm going to choose these two scenarios. They have both 50% effectiveness, but different baseline disease prevalence. So 6% baseline disease prevalence on the left, after intervention that goes down to 3%, on the left 20 going down to 10. And what we're going to see is that the sensitivity to one parameter is going to depend on the other parameters. If we look at point A, which is the scenario 1 baseline, in terms of coverage on the x-axis, so what fraction of the population is included in the study, and compliance, so what fraction of people that in the study received and were using the intervention. The color scheme here is the change in intervention effectiveness. If you go all the way to yellow, that's 100% effectiveness, so a full 50 points up, and the dark purple is 0% effectiveness, you're not reducing diarrhea at all. And if I look at this scenario 1 baseline, I can see that I have a really high sensitivity to coverage at this point. So a small increase in coverage is going to get me a really big change in my intervention effectiveness. But I can crank my compliance all the way up to 100, and it's still not going to give me perfect diarrheal disease reduction. Ooh, things are happening. Okay, well, let's see. Great. But if I were to look at this other point that also gives me 50% reduction, I see that my coverage is now not very sensitive, and my compliance is. In some sense, this is maybe not surprising, but it gives us a quantitative place to start investigating. If I were to now compare the scenario 1 versus scenario 2, so I've changed the rest of my parameters, not just compliance and coverage, I can see that these sensitivities are changing even more. So the gray here represents places where you have perverse scenarios. That means the intervention is like reducing effectiveness, or is like by giving the intervention, you're taking away wash infrastructure, which doesn't really make sense. So we can see that in the scenario on the right, it's harder to get improved effectiveness regardless. And remember, that was the one when we had higher baseline disease prevalence. I can look at a different set of factors here. Now I'm looking at the intervenable fraction. That's completeness. That's how much of the transmission could be reduced with a perfect intervention. And so if I have 100%, that means that everything, all the pathways are being reduced by my intervention. 0% is all the transmission is on stuff that I'm not intervening on. Baseline conditions is what fraction of the population already has a intervention grade equivalent. And what's interesting here is that if I, in scenario 1, increase my baseline conditions, so if I had the same location but had more people were beginning the study with the intervention, I can improve my intervention effectiveness. But in scenario 2, strangely, that if I were to increase the baseline conditions, I'm actually reducing the intervention effectiveness, which needs, you have to sit down and think about it for a little bit. And part of what's going on here is that the baseline disease prevalence is not fixed in these scenarios. So it's actually, you're reducing both the baseline disease prevalence and the intervention, but they're reducing at different rates. And so we're interested in projecting an intervention's effectiveness for any given context. And so we've developed this public use tool to hopefully facilitate this intervention planning for local contexts. I've left this QR code up over the next couple of slides, so if that's of interest, you'll be able to check it out there. And so what you're going to be able to do here is play around with some of these factors. This is just a couple of them that would fit on the slide. So you can change your baseline conditions to reflect your local context. You can change the intervention compliance. Also keep in mind that the more efficacious your intervention is, perhaps the lower the compliance is, because there are these trade-offs between high tech or high use or high difficulty to use interventions that make it less likely to actually be used as intended or to break it. The tool will calculate your prevalence, both in the control and intervention arm, and give you some basic statistics. And then you can look at the sensitivity of the intervention to each intervention and contextual factor. And this is largely meant as kind of a planning tool to kind of understand for your specific context, where is it worth putting more energy and more of your resources? Do you want to have higher compliance? Do you want to have higher efficacy? Do you want to have higher coverage? And so, in many ways, this is not surprising that the sensitivity of these intervention effectiveness to an intervention is highly sensitive to all of the parameters in your system. And I think it's useful to be thinking about the heterogeneity of these trials that I showed at the beginning in the context of this both intervention heterogeneity, but also contextual location heterogeneity. And so we want to account for these local contextual factors very specifically when developing interventions for those locations, and not just assuming that an intervention in one location is going to port over well to another. And so we hope that mechanistic modeling in this case can aid both in intervention planning and to estimate how the intervention results are going to generalize to another context. So just want to thank the collaborators, both at University of Michigan and Emory University, and partners at IDM. And this work was funded by the Bill and Melinda Gates Foundation. So I will stop there. Here's our Shiny App tool again, and we have a preprint available. So thank you so much. I'll let you pick, Alicia.
So Ani first.
One quick question and one maybe longer one. One is, maybe I missed this, but how did you parameterize the transmission rate of the pathogen when they're sharing the environment between intervention and non-intervention? And then I might be wrong, but if I recall, like at least Wash Benefits Kenya was done in a pre-rotavirus vaccine introduction world. And now that rotavirus vaccine has been introduced in many countries where, a lot of WASH progress needs to be done. What is your anticipated utility of your tool, considering rotavirus vaccine has, effects not just for rotavirus, but we've seen reductions in all cause?
Great question. So the first answer to the first is that we parameterized by a basic reproduction number that controls the let's say disease pressure. And again, it's not going to be pathogen specific, at least at this level where you're just measuring diarrhea. This will generalize to pathogen specific infection, but I think that's kind of, trials are not quite there yet, although I think they will be quite soon. The second question about kind of pre-post rotavirus. So Alicia has actually been doing quite a lot of work in this space with Wash Benefits Kenya. So Wash Benefits Kenya had completely null results in terms of diarrhea. And so thinking about how these contextual factors change, not only in terms of things like those WASH conditions, but in terms of the baseline disease prevalence, which I think is what most directly is going to be affected by the rotavirus vaccine. And so we have to think about, what if we had done the same trial again today in the context of a lower disease burden or a different pathogen distribution? Great.
Thanks for the great presentation, Kristen Aimjoy at UC Davis. So I'm curious what, if you at this stage could incorporate measurement noise of the outcome into your modeling. And the reason is that many of these studies measure diarrhea using caregiver reported symptoms. Sure. And that was way back in the day, the focus of my dissertation research and just how prone to measurement error that outcome is. We did a validation study in Ethiopia of caregiver reported stool consistency. So for those of you that don't know, the outcome measure, the definition is 3 or more loose or watery stools in a 24-hour period, which was kind of manufactured back in the 80s and doesn't really have any kind of clinical basis. So we did this validation study and we found that a few really interesting things. One is that the sensitivity of caregiver reported stool consistency was about 15% compared to double graded stool consistency. And so my hypothesis has always been that there's so much measurement error of the outcome that even if there was a true effect of the intervention, that you couldn't pick it up because there's just overlap. We also found out through that study that there were 16 different words for diarrhea. I might be misremembering the number, but more than 10 different words for diarrhea in Amharic, and a whole cascade of different ways that you can describe diarrhea, from like acute infectious diarrhea to just like loose stool that you'd have after eating, spicy food, for example. So I'm curious if you've thought about that and if it could be incorporated. Yeah,
absolutely. So the one thing is that we're working here, we have to work with what was measured by the trials. And so if the trial measured caregiver reported past 7-day all-cause diarrhea, that's what we're working with. And so if there is associated noise with that, it's kind of baked into the system. What I would love to have is infection data, which is kind of more direct to the underlying mechanism of disease transmission in the first place. And so, and then to your second point about kind of, multiple words for things and are you actually asking correctly? I think it really speaks to the importance of having multiple partners in designing these trials who have that really important local context, as well as the trialists who know how to design these kind of large studies, and hopefully we modelers who can also help to design intervention parameters. So thank you for that question. Happy to talk more and pass it on to the next person because I know we're running out of time.